This is Skandan, Dhruv, and Abhinav. We are going to present our course project for the randomized algorithms course. Our project is based on the concept of using randomized rounding to develop a fast solution, a fast but probabilistic solution to integer linear programs. So, 0, 1 integer linear programs have been shown to be an NP complete problem. And though there are many existing solvers for them currently, the time complexity can rise almost exponentially for a large set of variables and constraints. And ILPs are a very important set of problems to be discussed because they have a very wide variety of very wide variety of uses in problems from graph theory, combinatorics, and optimization. So our project is specifically concentrating on the problem of VLSI rounding, but the same concept can be extended to various different kinds of ILPs. So the setting of problem is as follows. We have an n into n square grid, and this square grid represents the space in which electrical components of a VLSI circuit can be placed. And there are a bunch of netlists to be arranged on this square lattice. And the setting of the problem is that there are a proposed set of trees which are supposed to span each of these all the edges in the netlist, and we want to pick exactly one netlist, one tree for each netlist, such that the weight on and all on the maximum weight on any edge is minimized. So the rationale behind this is to have as less of a probability on failure as possible. So so initially we relax the condition for the integer linear program into a rationalized linear program, and we allow the binary variables to take a continuous value from the range 0 to 1. So the binary variables here are representing are xij, and they represent if the jth tree for the ith net is chosen or not. So so first we take the constraints and use a rational LP solver, which should be theoretically able to solve the problem in polynomial time. And then using the resultant rational values we get for xij, we perform the rounding process on these values. So with these values as the parameters for a Bernoulli trial, we set each corresponding binary variable in the integer program to 0 or 1 with probability xi hat, where xi hat was the solution of the rational linear program. And since we have the constraint that there should be exactly one value set to 1 for each netlist, we first round all the values, and then among all the values that were rounded to 1, we randomly choose one value and pick that as the tree which is chosen for that. So these are some of the bounds which were obtained from the paper. So using some Chernoff bounds, the authors were able to show that with the if the rational optimum solution is W1, and as long as W1 is greater than or equal to 3 times ln of 2n into n minus 1 by epsilon, where n is the dimension of the grid and 2n into n minus 1 is the total number of edges in the grid. We have the following guarantee on the solution, on the optimum solution given by the randomized solver, in terms of the solution of the best possible solution given by the rational solver. So we have W1 plus square root of 3W1 into ln 2n into n minus 1 by epsilon. With probability at least 1 minus epsilon, we will be guaranteed that this particular bound won't be exceeded. So by setting epsilon to 1, we also get a guarantee on what is the maximum possible value that the solution of the integer solver can take. So in general, integer linear programs have a large class of applications like knapsack, job scheduling, and TSP. So, and this kind of formulation can be widely extrapolated for various different kinds of problems. So now I move on to the LP formulation of this problem. So first we have Xij represents whether the jth tree is chosen for the ith net. So the first constraint we have is sigma Xij over j should be 1 for all I, and we also have to now we have added some extra constraints in our implementation. So for each edge we have to calculate the weight of that edge, and that's essentially done by summing all indices ij where the edge e belongs to the tree tij, and we sum over all xij, and that's determined to be the weight of a particular edge. Now, among all the edge weights, we want to choose the edge with the maximum weight, and minimize the weight of that edge. So here we try to use linear constraints to find the to make a particular variable take the value of the edge with the maximum weight. So we do that in the following manner. So we define an extra variable u, and u is going to take the value of the edge with the weight of the edge with maximum weight. So the first condition we have is u is going to be greater than or equal to the weight of all the edges, and u is going to be at most we plus 1 minus be times m. So b is basically a binary variable for each edge, representing if that edge is the one which has the maximum weight or not. And capital M is just a constant large enough. It can be, as long as it's something that is at least the size of the nets, at least the number of nets. This inequality will hold. So the reason why we do this formulation is if BE is 1, we get u greater than equal to WE and u less than equal to WE for that particular edge. That will force u to be equal to WE. So you would take the value of whichever edge has B equal to 1. And for all the remaining edges, we need to have B equal to 0, because we have the additional constraint that the sum of all these binary variables across all edges should be 1. So for the rest of these variables, it should be 0, and we'll have u less than equal to WE plus capital M, which is trivial because u is less than or equal to capital M anyways for all the edges. And so using this integer, using these constraints, we use the CBC solver, and the cost function over here is to simply minimize u, which is storing the value of the maximum edge weight. So after this, we run this through a CBC solver, and we were able to obtain an integer, an ILP solution, which we'll use as a metric to compare our rounding solution. And we'll also get the rational solutions, which we'll use for the rounding algorithm as the weights for the Bernoulli trial.
Okay, next we'll move on and discuss the implementation of the algorithms. So we have implemented the algorithm specified in the paper, and we have also suggested an alternative algorithm of our own, which makes use of the algorithm given in the paper. So we have implemented the given algorithm using the LP formulation mentioned by Skandan, and we have used LP solvers such as CoinCBC. We tested our algorithm on 3 forms of input: random inputs, worst case inputs, and inputs that have large number of collisions. One more important thing to note here is that we need not restrict ourselves to trees as inputs here. This can be generalized to a problem in which we need to find sets with low intersection. However, for the VLSI specifically, in real life applications, we require inputs to be of the form of trees. So next thing, we have proposed an alternative algorithm. The alternative algorithm makes use of multiplicative weight update as well as the algorithm suggested in the paper. So we start off with any value of eta, which we refer to as the reduction factor. Here it is 0.3, and let R be the matrix that we obtain after relaxing the integer problem and solving it using an LP solver. Um, we repeat a certain number of times. Here we have kept it as 3, but we can repeat more times. uh, what we essentially do is, on every repetition we check if the newly obtained solution is greater than our current solution. If that is the case, then we penalize the newly obtained solution by reducing the probabilities of the trees chosen in the newly obtained solution. We reduce the probabilities by multiplying them by a factor of 1 minus eta. The idea behind this is that this will allow the solution to converge to a 0-1 solution, and we keep repeating this either a fixed number of times or until we keep repeating this a fixed number of times. um, as explained, the intuition behind this is that this will allow the algorithm to converge to a solution in which one tree has high probability of being chosen, because if the relaxed solution returns a matrix in which no one tree has a high probability of being chosen, then it is possible for the randomized rounder to make several mistakes before it actually ends up selecting the optimal integer solution. We tested out this input for various values of the reduction factor, mainly 0.2, 0.3, 0.6, 0.8. We tested it out on various forms of inputs, and for each of the inputs we found which value of eta gives the best performance, and we have used that for comparison with the randomized round. Next, we will move on to the empirical analysis. In the empirical analysis, we have defined a term performance ratio, which is the ratio of the solution obtained by the algorithm in consideration to the optimal solution produced by the ILP solver. And all the running times mentioned have been scaled to seconds. So we analyze our algorithms on 3 forms of inputs. One is a random input, one is worst case input, and one is a high collision. So to generate the random inputs, we choose a depth for our tree uniformly at random, and we choose a starting point for our tree as well on an n cross n grid uniformly at random. Then, starting from that root, we begin a BFS, and every time we choose a neighbor with some fixed constant probability, and we keep doing that until we have no longer any neighbors to choose, or we have hit the maximum depth. As you can see, here's the progression of the BFS tree on a grid of size 6 by 6. You observe that you initially start with a root having three neighbors chosen, and then those 3 neighbors choose more neighbors. But notice that all of the neighbors are not chosen because the neighbors are chosen with some fixed probability. The algorithm's performance was measured on 2 different types of random inputs. One were dense random inputs, in which number of nets and number of trees per net were both O of n, while the other form of input was sparse networks, in which both of these quantities were O of log n. The time measured for ILP solver was simply the time taken by the ILP solver, while for the rounder and the MW rounder, it was the time taken by the LP solver on the relaxed version as well as the rounding time. So you observe that for dense graphs, the performance ratios don't differ much between the MWU and the randomized rounder. But for sparse graph, there is a considerable difference because the MWU rounder reaches performance ratio of 1 on many more values of n as compared to the randomized rounder. If you compare the running time, as expected, the ILP solver has a larger running time because it is an exponential algorithm, while the LP solver is a polytime algorithm. But as you observe, for dense graphs, the running times do not differ by much, while on sparse graphs, the difference in running times between the ILP solver and the randomized solver is noticeable. We didn't analyze running times for MW solver because it anyway utilizes the randomized solver, so it will have the same running time as the randomized solver. With regards to the performance ratio for the randomized solver was obtained by, for any one input, considering 3 different instances of the randomized solver and choosing the minimum solution given by the 3 instances. Since the solvers start taking large amount of time for larger values of n, we have bounded our analysis to values of n up till 30. As the timing analysis suggests, the randomized solver is faster because it is a polytime algorithm as compared to ILP, which is an exponential algorithm. Another thing we analyzed was whether the randomized solver lied within the bounds lied within the bounds suggested in the paper. For this, we found the distribution of the inputs of the randomized solver and checked for various values of epsilon varying from 0.1 to 0.9 whether 1 minus epsilon fraction of those values lied within the bounds given in the paper. And as you can see, for all of these values of epsilon, we find that the output at least 1 minus epsilon fraction of the output lies within the required bounds. So we see that the analysis given in the paper holds.
So the second type of input we analyzed were worst case inputs. And to generate the worst case inputs, what we wanted to do was come up with a sort of input which would fool the LP solver into distributing its nets. So for a single net, you would have multiple trees, and we wanted it to set a fractional value for as many trees as possible, so that the rounder would have multiple options, and then there would be a high probability of collision, while the ILP solver would only assign a single tree, for instance. So the way we did this is we started with n-1 nets for an n cross n lattice. And as you can see here, each net consists of one column, basically, the starting and ending points of the column. And then we generate n possible nets, which basically go to the side and use a different column to connect those two nodes. And this is for every net, you have these many trees, you have n trees. And then we generate 5 different nets for any pulses. And the reason we generate n-1 nets is very important. So I'll show it here. Basically, when we generate n-1 nets, the ILP optimum would be 1, as seen in this figure. You can always just take the column. But the LP optimum, the LP solver could assign a 1 by n weight onto every tree. Since there are n trees, this guarantees that every net has a total weight of 1 assigned to it. But now if you consider any single edge that is a column, it has 1 by n into n-1 will be the total load on that. So you get n-1 by n, which is actually less than 1. So the LP solver would get a value less than 1, which means now it's more likely to actually distribute its values among the different trees. And that leads to high collisions from the rounding process. And it very rarely gets to the ILP. So as you can see, when we actually analyze this, the first thing we did is we did not run the ILP solver because we know that the optimum is 1 by the way that we generate this input. So we looked at the MWU with a reduction factor of 0.2 and a randomized solver. As you can see, the performance very rarely touched 1. The minimum was usually 2. And as we increase n, it goes higher and higher. The randomized solver even touched 7 times the optimum, which was basically 7, which is very bad performance. While the MWU hit a maximum of 5, and it seems to perform a little better on average, but not very better. For the running time, we only took the running time of the randomized prompting algorithm, not the MWU. As I said, we didn't run the ILP because we knew what the solution was going to be. And surprisingly, the running time was actually pretty fast. Even though this specific type of input is kind of a dense input, it still ran within 4 seconds for the 15 to 50 ladders. Now, this is the output distribution we got for these worst case inputs, but we couldn't verify the bound given in the paper because since the LP optimum is itself very low. It's actually lower than the required amount for the bound, which was, that was mentioned above. Basically 3 into ln 2 and n minus 1 by epsilon. That doesn't hold for any epsilon, so we can't analyze the bounds, but as you can see, in general, you get around 6 times, and this is for n equals 50. The third type of input we created is high correlation inputs. The reason for this is that we realized in the randomized input generator, we usually got an integer optimum of 1 or 2, and it was very well to get an optimum of 3 even for very high dimension lattices like 13 to 30 because of the randomness that kind of made it sparse. So what we figured is, let's find a way to generate very high correlation inputs where even the optimum is high. And the way this was done was, we chose a set of k edges, and then every net trees would share the same k edges. So if a net has 3 trees, we would assign k by t edges to that tree, and then we would simply shuffle the k edges that we chose and assign them to all of the trees of that in some order. But basically, all nets use the same edges for the trees, so even the optimum would have a high correlation. We estimate that the actual expected number of opt would be Tn by k, where n is the number of nets, t is the number of trees per net, and k is the number of edges we choose individually. And we noticed one more interesting thing while running the program on this input. What we noticed is that sometimes the ILP solver would assign 1 to some particular trees and get away with it, like it would get a good optimum by doing that. But a rational LP solver would assign 0 to those exact same trees that were assigned 1. And because of that, the rational solver would never converge to the exact optimum. So as you can see here, we plotted the number of trees that the ILP took as 1, but the relax solver did not, as in the relax solver set it to 0. And it seems to go with it on average. And this is the way the solution worked. The integer and the rational solution changed like this. So as you can see, our expected number is linearly net, as we thought. Once again, we did not analyze the bounds here or the timing, but this particular thing can be seen to be sort of a sparse all dense graph based on t. So you could expect those same kind of performances. Now, another thing is, sometimes we really want to get the optimal solution. We don't want to get within, say, 2 times the optimal solution. We want the optimal solution. So another thing we measured is how many times do we need to run this program until we get the actual optimum. So if we're running just the rounder, we run the randomized rounder k times and take the minimum answer, or we run the MWU for k iterations. And what we found is that in general, the rounder for high correlation inputs takes around n iterations to get to the optimum, while the MW rounder takes n by 2, which is still the same order of magnitude, but it shows that the MW performs slightly better in terms of average. But both of them sometimes fail to find a solution, and MW can also fall sometimes into local optima and not come out of there, which is a slight disadvantage. So our conclusion is that the rounding algorithm in the paper does seem to work on inputs. We generated 3 different kinds of inputs and tested it out on all of them. We came up with the MWU modification that seems to perform better in some cases, like the worst cases, and in other cases, it never performs worse than the randomized rounder. And a last thing that we found from the high correlation inputs is that the MWU rounder sometimes falls into local optimums because it sets some variables as 0 when the integer solver sets them to 1. So one possible modification we could explore in the future is, what if the MW rounder also excited some 0 variables to non-zero values if it did not detect any improvement after a few iterations? That's that project. Thank you.